today is this project that we've been doing at the University of Minnesota for quite a while now, and only now, after about 10 years, have we been able to come up with sort of a catchy acronym. Because I think a lot of the projects, if you want them to succeed, you have to have a catchy acronym. So we've come up with C3PO, which is Customizable Computer Coaches for Physics Online. And as long as we don't try to make any money off of it, maybe Lucas won't come after us. Okay. Okay, so some of my collaborators, there have been a lot of people working on this project. We've been doing this for a long time. In terms of faculty, Bijaya Ariel, who's a professor at the University of Minnesota in Rochester, Ken Heller, who's also in the Twin Cities in the physics department, and myself. And I'm in the Department of Post-Secondary Teaching and Learning in the College of Education. There have been a couple of postdocs, Evan Froderman and Andrew Mason. Andy Mason is now at the University of Central Arkansas. Some graduate students, Ting Ryan and Jie Yang. A couple of systems programmers who are working with us. Some other collaborators. Jialing is in the STEM Center here on campus, and she's been coming to our meetings and contributing her ideas. It's nice in this mode that I can actually add on that we've got one more systems programmer that I should put on, Steve Klein. Lots of undergraduate programmers helped, and this work has been made possible from funding from the National Science Foundation. So let me talk about what we're trying to do. The goal here, and sort of a focus of the University of Minnesota's physics education program for a long time, has been trying to improve student problem solving. And why problem solving? I don't think I need to tell you guys why problem solving is important. You look at any of the numerous National Academies reports, there it is, in the framework for K-12 science education, the next generation science standards. Problem solving is everywhere. All of our jobs, our lives are pretty much problem solving. And so if we just want to formalize this a little bit, what is problem solving? A definition that we use a lot is from Martinez, from Phi Delta Kappa in 1998. It's a situation in which one does not know how to resolve. Because if you knew how to resolve it, it wouldn't be a problem. So it's something that you don't know what to do. And solving a problem requires making decisions. Okay, making decisions to specify goals, to figure out what assumptions you're making, identifying and applying useful ideas, connecting those ideas, evaluating the results. And physics, being sort of a gateway course to a lot of STEM careers in college, is sort of a natural place to teach it. And I think physics in high school as well, because many of the students who are interested in that also take physics in high school. And it's a great place to start helping students learn some more sophisticated problem-solving skills. Unfortunately, what we know is that, especially in physics, a lot of students have the impression that problem solving is applying a known formula or a pattern. And real problem solving, it's just not natural for most students or most people. It's things that we can certainly learn and improve our skills in. Some of the research behind this that I want to point out, the expert novice research, this is a long literature that goes back decades in problem solving. What we know about experts and novices. So what's the expert view of solving problems? Well, they view it as a process of making a series of judicious decisions. So at its heart, it's a decision-making process. They'll do things like perform a basic qualitative analysis of the problem before attempting to solve it, whether this is in physics or not. They'll do things like periodically evaluate their progress, try to connect it with their outside knowledge. By contrast, novices, especially in physics, they often view it as a matter of mathematical manipulations, and they'll plunge right into those manipulations. What formula do I need to use? Let me put numbers in it. I'm done. Okay. They don't spontaneously evaluate their progress or the answer. In terms of teaching problem solving, there's been a lot of research on this, and there are a lot of problem solving curricula, especially in physics, about how to do this. And the thing I'd like to point out is that all of these methods, either explicitly or implicitly, go back to cognitive apprenticeship. Okay? What's your familiarity with cognitive apprenticeship?
I'm familiar with their work.
Okay, so yeah, This is back in the 80s, Collins, Brown, and Newman. It's an attempt to bring learning is very diverse, and there are different learners, and there are different learning styles, but if you look throughout history, the one sort of thread through human learning that has been really successful is the apprenticeship model, right? So back in the old days, you want to learn to become a tailor, you become an apprentice to a master tailor, you sit in their factory with a lot of other apprentice tailors, and you learn different skills. So a cognitive apprenticeship is just an attempt to bring that features of a traditional apprenticeship to combine that with elements of schooling. Okay. Some of the elements: modeling, coaching, and fading. So modeling is where the master tailor, let's say, would show the apprentices, here's what we want you to do. Here's what you need to be able to do. Coaching is where the apprentices try to do those tasks on their own with help and supervision from the master. And then the fading is where, as the apprentices get better and better, the master withdraws the help and they eventually become masters on their own. They become much better, they can perform independently. Scaffolding are just different kinds of tools that might be introduced at different stages to help the students with learning the tasks. And cognitive apprenticeship is really it's modern in the sense that it's consistent with the biological view of learning. I mean, we now know something about the brain, and that knowledge is really just sort of the pattern of neurons and their interconnections in the brain. Learning is the rewiring of what those connections are. And so if you want to teach someone, one of the best ways to do it is just put them in an environment where they have the opportunity to rewire their neurons, to make those useful connections, and thus learn a new field. And so that's what we talk about. That's what we mean when we talk about learning in an environment of expert practice. In traditional academic classes, time available for students to engage in coached practice. Especially if we talk about the higher education where you've got a physics lab with 200 people in it. Individualized coaching, which is one of the critical components of a cognitive apprenticeship, very limited. I mean, you have smaller lab sessions and discussion sessions with TAs with maybe 20 students, but it's still hard to do. And so that's where the computer coaches come in. What we're trying to do is design something that can fill that need. For this coach practice. So the coach is designed to support and augment learning of problem-solving skills within this cognitive apprenticeship framework. And so what computers can do is they can provide on-demand coaching. Okay? If a student wants to practice at 2 a.m. in the morning, because that's sort of what their schedule is, computers are available. Computers aren't going to complain. A computer is sort of infinitely patient. It can be seen by students as being non-judgmental. And so there are all these kinds of advantages that a computer can have over a human. Of course, they might not be, at least for a while, until the technology and the science gets there, they might not be as good as human tutors. But certainly they can be much better than what is currently available. And other things, one of the hallmarks of a cognitive apprenticeship is you're trying to make explicit what are these thinking processes that are necessary to perform the task. I mean, for tailoring, you can see it, but for what's going on inside a teacher's head when she or he solves a problem, you really can't see that. And so a computer can help make this explicit. Let me just digress a little bit about this problem-solving framework. The problem-solving framework that we use in the physics classes here at the University of Minnesota, it's based on a generalized framework that works in all fields. Also, if you look back to 1945, Polya's How to Solve It book gives a very nice sort of generalized framework for this. A number of different steps in this framework. The first step is to recognize the problem, which we call focus the problem. So, what is the problem? What are my goals? What are some of the assumptions that I might need to make? What's going on? What do I need to get? The second step is describe the problem in terms of the field. So if we're talking about physics, what are some of the physics concepts that might be applicable? And in what ways might they be applicable? Plan a solution is to now, I know which physics concepts are applicable. How am I going to put them together in order to get what I want? Execute the plan is, let me now carry out that plan, get what I want. and then evaluate the solution. What have I got? Does it satisfy the requirements? Now, having a 5-step framework like this in no way means that it's as simple as following 5 steps. I mean, we all know that in real problem solving, you get stuck, you go down blind alleys, you have to back up, you have to do things over. And so these are just 5 pieces of a framework where one has to go back and forth and realize that it's never simple.
Is the coach,
yeah.
That last statement there requires the continuous reflection and iteration. Is the coach itself is the computer coach adaptive to me as a particular learner?
So as I'll show you, the version 1 coaches that we've tested so far are not.
Okay.
But then the version 2 that we're planning and working on, that's one thing that we want to put.
Okay.
Yeah. So let me show you some of these coaches. And these are the version 1 coaches. We got 3 types of these. And this is based on the reciprocal teaching framework, Palinsar and Brown, which was originally developed to help middle school students read with comprehension. So there's 3 different interaction modes. In a type 1, the computer acts as the coach for the student. So the computer's the tutor. In the type 2, we turn it around. We have the student act as the coach for the computer. So the computer pretends to be a student, and the student has to help the computer solve a problem. In the type 3, this is where we start to withdraw the help. This is the fading, where the student works more independently and the computer provides feedback if necessary. And one of the parts of our philosophy here, le mieux est l'ennemi du bien. So the best is the enemy of the good. Well, if you want to have the best possible thing, it's going to take ages. So what we're trying to aim for here is something that works well, right? We know developing effective coaches is this iterative process. It's a cyclical process of development and testing and thinking about how this works. So, version 1, here's our attempt. For the coach demo, there's a couple ways we can run this. They're on the option number 1 is you could watch me, and I've got a couple things set up at different points, so we can look at these and go through them. Option 2 is you can ignore me for a while. If you have a laptop, you can get on the network, and the coaches are on our research page here, groups.physics.umn.edu. I'll have this website on at the end also, so you can write it down, and you can try some of the coaches. I know I've tried it myself with this U of M guest network. The bandwidth is limited. There's 100 people here, so it's going to be a little slow at first. But then here are some sort of recommended sequences. Do you guys have a preference?
Oh, I guess in the spirit of hockey, how about the sliding puck? Is that what you're looking for? Conservation?
Yeah, so the ones that I have prepared, and I have them sort of at different points, so we don't have to work through the whole thing to get there, are the ones from the conservation of energy, in fact. So the sliding puck, the skate loop, and the bungee jump. So let's just take a look at those, and let me show you what these look like, because it's hard to think of them in the abstract. This first thing, this is the web page that has all the coaches. It's really snazzy and fancy, as you can see. But it's a sub-page of our main physics education research page. And so you can look at our research, and then here is that project, the Internet Computer Coaches. So to look at some of the coaches themselves, well, let me start from here. Okay, so the sliding puck, actually, let me do it this way. Let me go back to this page. The research, this, and then from here, if we just scroll down to sliding puck, and I click on that, that brings up the screen with the coaches. Okay, so there's a start screen. There's just a one-screen thing with some instructions for students. I mean, one of the things that you really want is you don't want to need a manual, or it has to be as self-evident as possible. So we just try to tell the student, well, here are where things are, and here's where you get the feedback from the computer, and you click these buttons and things like that. So we'll begin. And this is sort of an overview. On the left side, we can see this yellow index bar, which tells students where they are in the framework. These coaches are keyed to the Minnesota problem-solving framework, which is what we use in the physics classes. And again, right now, it's not modifiable unless you know something about coding and Flash programming. But for the second version, we're working on something where this is all done using a graphical interface so that even instructors who don't have any programming knowledge, they can put their own together. They can modify ones that we build. So it goes through a framework. The coaches don't try to teach the framework. We assume that happens in the classes. So these are to augment the classes. They're not standalone. Things. And so we start out where we have a question here, and this is the problem. This one is at a state fair. You see people trying to win a prize at a game booth. They're sliding a metal disc shaped like a puck up a wooden ramp so that it stops in a marked zone near the top of the ramp before sliding back down. You estimate that you can slide the puck at 8 feet per second, but would that win the game? The two boundaries of the zone appear to be at 10 and 10.5 feet from the bottom of the ramp, where you release the puck. The ramp appears to be inclined at 37 degrees from the horizontal. You happen to remember that between steel and wood, the coefficients of static and kinetic friction are 0.1 and 0.08 respectively. The weight of the puck is about 2.5 pounds. Okay. And we can talk a little bit later about the structure of these problems. It's something that we've developed called context-rich problems. But the first thing that we try to do, okay, so the first step is, of course, focus the problem. And so what is going on in this problem? Physics teachers always tell students to draw a picture. Draw because you want to know if you know what's going on or not. So what we do is we've broken this task of drawing the picture down into these much smaller tasks. And in this type 1 coach, the first question is, what do you want to draw in the picture? Do you want to draw the puck only, the ramp only, or both the puck and the ramp? If you click the puck only, well, this is not an optimal solution. I mean, it's not wrong because there are many different ways to draw the picture, but there's probably better things there's probably a better answer. So we include some feedback down here. We say, try again. Since the ramp determines the puck's motion, it is relevant to the problem, it should be included in the picture. So we try to give students that kind of feedback. Both the puck and the ramp, now we turn green. Okay, let's go on. Lots of different decisions in drawing a picture. Do you want to draw it from the top view? Do you want to draw it from the side view? Top view is non-optimal. I mean, it's not wrong. You could do it. But again, we sort of give this yellow feedback about, well, there's a better answer. We can do it from the side. And then we start to put the picture together. At what positions do you want to draw the puck? You could say at the bottom of the ramp while you're pushing on it, just after you release it, midway through its motion, when it comes to the highest point on the ramp. Students could check any or all of these. And again, this is sort of non-optimal. There are places that are definitely necessary and much better for solving the problems, some others that are not quite as necessary. So we give the students this kind of guidance in drawing that. What kind of assumptions should you make? Because a lot of these are very important in physics. Are you going to neglect air resistance? Beginning students often worry about air resistance because it's a real force in the real world. What assumptions are we going to make so that we can actually solve it using what we know? Size of the puck can be neglected. I've checked here, friction between the puck and the ramp can be neglected. If I say done, well, now this is actually wrong. We can't neglect friction between the puck and the ramp. So this is a different kind of feedback. It's not just non-optimal, it's actually wrong. So we have a red feedback thing there. And so we get past that part, and now we start including things like lengths or distances on the picture. Here we'd like to know the distance traveled by the puck, and so we start to put that in the picture. Any velocities, is that going to be something that's useful? Yes. And again, we break all these things up into smaller steps about what are the velocities, and then it starts putting those in the picture. Okay. And again, if there's anything that's actually wrong, we give the student that kind of feedback, and so they can choose another answer. And so they work through it like this to build the picture. Just different questions about now it's time to put accelerations in the picture. What's the direction of the acceleration at these 2 points? Things like that. And so this proceeds like that. They go through and they put kinematics quantities, the motion quantities. They go through and they put information about forces and then some of the other information there. A little bit later on, Let's see, right here. So here's the point at which they've now fully constructed the picture. You can see what that looks like. They've determined the question. What are they trying to answer in this? And this is still part of focusing the problem. Now it's time to try to figure out what kind of physics approaches might be useful for solving this. And we built these coaches, these version 1 coaches, with as much flexibility as we could. I mean, of course, you can always put more, but how much work are you going to put into this? And so actually, any of these different kinds of approaches, kinematics, dynamics, or conservation of energy, are useful. And so we've made it so that students can choose any of them. Okay. So for example, if they choose dynamics, which is using Newton's laws to analyze the situation, we then go through, well, how are you going to apply Newton's laws? To what system are you going to apply it? At what time do you want to apply this? And there are wrong answers, and there are better answers, and there are good answers. And so once they finish that, the next step, describe the physics, says to take this information and to now put it in the language of physics. Okay. So again, very common practice. Let's draw a free body diagram. Okay. And we try to make these connections. So we have the picture that the students have drawn up here, and here's the diagram that they're going to put together. And so we want to emphasize to the students that the picture isn't just for fun or because we're trying to make you suffer. It's actually useful. So in this diagram, if we want the forces, let's connect it by selecting the elements from the picture that go in the diagram. And so they can select the forces, and those are all automatically translated into the diagram for them. And they might say, okay, well, I've got my diagram done, but, well, that's not everything. If you're going to use Newton's laws, force equals mass times acceleration, it's probably also good to include the acceleration. And so we go through that, and it helps them, figure out how to use Newton's laws in this. How do we then go through this diagram, choosing the angles that are necessary, decomposing forces into X and Y components, and all of these things. There are different kinds of multiple choice questions. There are multiple select questions. So let me get a little further, breaking that weight force, the gravitational force, into its components, trying to figure out what's the quantitative nature of those components, cosine theta, sine theta. And so it just sort of goes through that. And it'll do that with any of the different approaches that students try. If they want to use kinematics, if they want to use conservation of energy, same kind of thing. That's what it does. And then a little bit later, that's not the one I wanted. The one that I wanted is here. A little bit later, this is the plan the solution, where now students have the equations that they developed from the diagrams, again, using the diagrams to instantiate the equations, and now it helps them with the algebra. The algebra help is pretty limited, and we would say with the version 1, that's one of the weaker points. If students come in having trouble with doing the algebra, it's not really going to help them. Okay? But what we hope is that they will be able to identify where they need help and find a human who can help them. Just to show you some of the other types, this is, let me go to this one. So this is one of the second type, the one where the student coaches the computer. So, like many students, the computer starts out with, well, I don't know where to start. What should I do? And we have a number of approaches that the student can do. Maybe the student wants to write down the equations. I want to write down the quantitative relationships. So maybe the student tells the computer, you should write those down. And this is very strongly discouraged. No, before you write any of these down, you have to do this qualitative analysis bit so that you know what's going on. So we essentially force the student to go through sort of a productive means using the framework. And so the computer will draw a picture, the computer will decide on some of these assumptions, and the student has to sort of okay that's what they are. Sometimes they're not okay. They'll get feedback on that. Have I drawn all the objects? Is my picture complete? Well, no, you actually should put more things in it, like the forces and the motion quantities. So we do that, and sometimes the computer deliberately makes mistakes. So for example, here, the motion quantities that are there, some of them are wrong. So if the student says, well, these quantities are correct, no, some of them are not. So the computer actually has two roles. One is as a student, and the other one is sort of as a general overseer. And the student then needs to go in and select what is wrong. What's wrong with my picture? Well, the student has to go through, well, okay, so I see that the final velocity of the skater at the top is not in fact 0. So I have to point that out. And the acceleration is not in fact 0. And then after that, the computer has to help the student has to help the computer fix those. Well, the velocity is not 0; it actually points in that direction. Although we do not know the magnitude right now, and the acceleration actually points in that direction. So going through and helping the computer fix that. And these errors that the computer makes are key to things that we know students commonly have difficulty with. Let me just show you a piece from the third type. The third type is one where the student works more independently. So here we give the student a problem. This is a problem about a bungee jump, and we say, have at it. Put in your answer, and we've built sort of this calculator interface where students can enter equations or expressions. So you could do something like that. And we really want to check to make sure that the student has gotten the right answer for the right reason. So we're not just going to say, is this right or not? We're going to say, well, let's go through and let's check some of your steps. So first of all, we expect that in order to have solved this problem, you should have had some kind of qualitative representation, like a picture. So I've got 4 pictures here. Which of these is right? And if the student puts one in that's wrong, well, we say, okay, there seems to be something wrong with your work. Okay, we're not even to the stage where we're going to check your answer. Let's check these earlier steps, because if you thought this was the right picture, there's something wrong. So we just give students a hint that they might want to work through the picture in question help session, and we toss them back to this stage where they can get help with any of the stages. Okay. Now, we've recommended where they might want to get help, but they could choose to get help at a later stage if they want. If they think, well, no, I just clicked that by accident, I really know what I'm doing, I want to go and get help with the equations, the quantitative relationships, the student is free to do that. Okay, so they can go there, and they can go choose that. But before that's a later stage in the problem. We don't want to help them with that if they've got earlier things, if they've got problems with the earlier things. So again, with these later stages, we try to check that they've got some of their previous work right. So maybe they do. They check some of the details of their approach. Again, if some of these are wrong, we give the student feedback again. Well, no, it really looks like there's something wrong with an earlier stage. Why don't you go back and take a look at that? And so students can really get help wherever, but we just always make sure that things are good at the beginning steps. They can always say that they don't want any help. They're going to try to find the error by themselves, go back and try to solve the problem again. If they get stuck and they just can't come up with an answer, there's always a button down here. I got stuck and couldn't get an answer. If they choose that, we just bring them to the help. So it's an attempt to really reduce some of the scaffolding that students get. Okay. So I hope that gives you kind of an idea of what these coaches look like. In the few minutes that are left, let me give you some of our recent results. And I'm kind of excited about the results because we've been working on this for probably 10 years, and my involvement with computer coaches goes way back to about 97. So to actually obtain some evidence of educational impact is really exciting for me. In terms of the software framework, we're using Flash and ActionScript. In terms of comparison, there's a lot of web-based homework systems out there. But we think that ours is much more thorough in the sense that the web-based homework systems that are out there are typically this is right or this is wrong. The student enters an answer, it's right or it's wrong. Some of them, like Mastering Physics, are more sophisticated. They have some tutorial problems. But we still feel that ours is superior in the sense that it really emphasizes the decision-making framework and just the generalness of it. That is the same decision-making framework for every problem that students are going to encounter. Whereas the ones on the web that exist right now are generally more problem-specific and tell students, well, you should think about this. And, well, maybe that's okay for now, but how would you ever know to think about that? So that's one of the drawbacks. There's a system out there called Andes, which is really sophisticated. It's sort of an intelligent tutor. And it's meant to be minimally invasive. It helps students. It's sort of electronic paper. Students draw pictures on it, define quantities, and use it to help solve their problem. And that has also got some positive evaluation results. It's much harder to use, though. There's an introductory video and some introductory problems that students have to work with. It's non-intuitive if you just start it up and try to use it. So we hope that ours is better in the sense that you sit down, you use it. Okay, so what are some of the research questions that we've been looking at over the past few years? We'd like to look at the characteristics of students who use the coaches, whether they think they're useful, and do they actually improve students' problem-solving performance? And what should we carry forward to version 2? What else should we modify? So in terms of the research studies, we've been looking at our calculus-based introductory course, just to have one kind of course to test this in. We've done it in fall 2011, spring 2013, with about 250 students in those 2 semesters. In both of those semesters, we had 35 of these coaching modules that students could work through. And we had assigned for homework problems that were these coach problems. And then we collected data such as pre-post scores, students' written problem solutions on exams, a couple of opinion surveys, and the computer actually tracks all of the keystrokes and clicks that students do. So we have that data as well. Very interesting, the user characteristics. So this is from the spring 2013. What we find is that there are sort of distinct populations in the class. Again, about 250 students. In terms of analyzing the data, we decided to break up the students into 3 groups. One group is this H group, which are the heavy users. These are students who use between 80 and 100% of all the coaches, these 35 coaches, representing 35 problems. About 49 of them, about 65% male, 35% female. Medium users who used in total between 40 and 60%. And light or non-users who use 0 to 20%. And a couple things you can see. This is the usage time versus weeks. So the heavy users sort of remained. They were using almost all of the coaches throughout the semester. We lost some of the data due to a server glitch in week 4, but we have this usage. The light users sort of had a low usage throughout the semester. The medium users, very interesting, start out very high, end up very low. Okay, so there are a couple of different interpretations you can give to this. You can say that, well, maybe they started out using them and then decided, these really suck, I'm not using them anymore, and that dropped off. Or, what we hope is more the case, is that they start off using them, they sort of see this problem-solving framework, and then they're better able to use it themselves without the coaches, and thus don't need the coaches as much. Another thing that I'll point out is, in terms of the male-female ratio, this is a college physics class. It is weighted towards male, but if you look at the light or non-users, there's definitely a much smaller fraction of female students there. The usage by the medium and the heavy users, they tend to be more heavily female. Other interesting user characteristics. We've done for many, many years this pre-semester survey about, what do students expect to earn, how much time do they expect to spend on this. The high students who use a lot of these coaches, okay, their expected study time, 6 to 10 hours or more than 10, they expect to study more. In terms of the expected grade, it's more weighted towards this B. Okay, no one expects to get less than a B. The average grade turns out to be about a B, B minus, but no one expects to get less than a B coming in. If you look at the students who use very few of the coaches, their expected study time is much less. They're much more confident, and they overwhelmingly expect to earn an A in the class. Some other things, if we look at their pre-test scores, the FCI is a physics conceptual test that many people use to sort of get baseline data about what the class looks like. And looking at this, the low users have a much higher pre-test score than the high users. So they come in with sort of better preparation in that sense. So some of these differentiating characteristics, gender, their pre-FCI scores, expected study time, expected grade, these are things that differentiate users from non-users. Perception of usefulness, because I'm running out of time, I'll sort of just give you a quick overview. Basically, students did think these were very useful. Among the heavy and medium users, it was among the top 3 components out of 10 in the class that we asked them to rank. We asked them to rank things like lectures, discussion sections, labs, the textbook, the homework. These computer coaches consistently showed up in the top 3. For the light users, as you might expect, the ranking is much lower. They didn't find them as useful. One thing I'll point out also is that there's a tutor room staffed by human tutors, and the coaches ranked as more useful than this tutor room for whatever reason. In terms of perceptions of usefulness, students disagreed with this statement that the computer coaches did not help improve my problem solving. So they thought they were useful in that sense. They agreed with the statement that they did help improve their conceptual knowledge. These are on the surveys. Now, whether or not they had an actual impact, again, in the time that's running out, just quickly, we looked at student scores on the final exam. And we looked at how they scored on the problem-solving part. So this is not multiple choice. These are problems that they solved. And we looked at their grades. Now, in the spring of 2013, that's this column on the right, if you look at the students who did not use many of the tutorials, did not use many of the coaches, their average grade is about a 70%. If you look at students who use a lot of the coaches, the average grade is 70%. Okay. So what does that mean? Does that mean that it didn't help? Or, well, to compare that, we did the following. So as I mentioned before, the characteristics that separate high users from low users are things like gender, pre-FCI score, and then the other two that I don't remember off the top of my head. So what we did was we went back to a number of semesters. So we took baseline data. This is about 3,000 students. And we tried to find students that were a one-to-one match with the students in the spring 2013 class based on FCI pre-score, gender, expected study time, expected grade in the class. And when we matched them, what we found over all those semesters, averaged over all those semesters, is that on those final exams, the students who came in, with a higher confidence, not using the coaches, who would not have used the coaches as much had they had them, average grade on the problem-solving part of the final exam, about a 72%. The students with characteristics of those who used a lot, 61%. Okay. We tried lots of different matching procedures to make sure this is not a fluke. This is about the same across each of these semesters. It's not just a fluke of a final exam or a particular class. This really seems to be a very robust result. It looks like just using these coaches has improved their problem-solving grade on the final by about 10%, which is a full letter grade. Okay. And you can ask, well, does final exam grade really reflect problem solving? This graph here just shows we've also developed a research-based rubric for evaluating problem solutions. And we applied that to a number of the problems on the final in a different semester. We haven't yet gotten the chance to do it with the spring 2013. But if we look at the correlation between this rubric score, which is based on sort of aspects of expert and novice problem solving, versus the final exam score as assigned by teaching assistants who knew nothing about this rubric. This correlation is sort of incredibly good for any educational. we can't believe it's this good. So I think we have some basis to say that, to make the claim that this is an improvement in problem solving skills. Some of the things that we want to do in version 2, ability for students to adjust the grain size. I mean, you can see the version, the type 1, it really drags you through every decision that's necessary. And some students need that, some students don't need that. And it's very painful to the students who don't need it. So the ability for students to adjust that kind of size. Greater flexibility in the problem-solving procedure. It's pretty linear. You know, you have to draw the picture first, but when you actually solve a problem on paper, there are several steps that you can do out of order that don't matter. So trying to allow students to do that. Most importantly, if we want this to make a contribution to STEM learning, if we want people outside of our one school to use it, we know no innovation goes unadapted, right? There are lots of different local conditions. Teachers have to be able to modify things to suit their own preferences, to suit their environment, and so on. And so that's a really important part of these version 2 coaches that we're making right now. It's a complete rewrite of the code. The important part is, how do we make it so that these coaches can be tailored by instructors with no programming experience? So just a quick summary as we're out of time. We've created a set of these computer coaching problems for problem solving. Students find these useful. And the other thing we find is that the students who tend to use the coaches, even when there's no direct grade benefit to doing so, tend to be female students, less prepared, less confident students. So we think that's useful. They do seem to improve students' problem-solving skills, and we're trying to replicate this. And version 2, with more flexibility, it's under development. We think we're going to have an operational version very soon, and we want to sort of farm this out to more places that are not the U of M, including high schools. We've written a number of grants to try to include some high school physics classes in our development. We're just waiting to hear. And as promised, this is, for more information, this is the web page that all of our coaches are on. And all 35 of our version 1.0 coaches are available. And this is our main research group page, the page that has the coaches on them. Again, you can access by first going to this research link and then the Internet Computer Coaches, or, and I should have put the full URL in here, the full URL to go directly to the coaches is this one that has prototypes.html on it.
You have mentioned the role of confidence a number of times in terms of predicting usage and so on. Did you do any measures of confidence of the students at the end of the course to see if...
So we had in our survey, we had questions like, the computer coaches helped me feel more confident about problem solving, or I don't remember the exact questions, but we had items like that in our survey, yes.
And you were finding that
I don't remember offhand, so I better not say, but it at least did not make the students' confidence go down.
Okay.
So I can't tell you for sure whether there was a significant boost, but I know that there was not a negative effect.
What is your role in this? Are you a developer? Or are you just...
So we have these weekly group meetings where we get together and we look at the coaches and we decide, what are the problems? What new features do we want in them? So I guess I and Ken and BJ and the postdocs, we're all developers. We're all contributing to it as the version 2 gets built. We'll all be trying to use it to build our coaches on our own and trying to figure out, well, what was non-obvious? What is hard to do? What's kind of clumsy to improve the interface?
A problem has a particular coach assigned to its presentation.
That's correct.
Or you don't have the 3-coach version for the same problem.
So with the version 1, each particular problem has only one type of coach associated with it. What we're trying to do with the version 2 is make it much easier to do so that it's easy to build different types of coaching. Yeah, with the version 1, one of the other drawbacks is we had a lot of undergraduate programmers, and even when they got proficient at it, it would still take them 20 to 40 hours to build a new coach, a new problem. And so, you can't expect any other teachers to do that. And so hopefully with the version 2, we'll have a big storehouse of our own problems that we've developed. Teachers can modify those or build something new, whatever they have time and the inclination for.
Thank you very much.
Sure, thank you.
So we can go up to that website and try them out ourselves?
Yes, and they're completely, completely available. And hopefully when we get the version 2 working and tested, we'll put that up there too. Our intention is sort of to go with an open source model. I mean, we're not that over, say, a commercial development, just to have it out there.
Are you going to be publishing the results of some of the study?
So these results we're writing up right now
Okay.
for journal publication. Yes.
Thank you.
Thanks.
Yeah, very interesting.